Okay, well, great. We're at week 3 Friday already, so and Happy New Year to those of you celebrating New Year's this weekend. And yes, if you have your homework, I will take your homework. You can turn it in right here. And if you don't have your homework, that's okay. You can submit it online before 6 p.m. and that's totally fine as well. So whatever you guys decide to do. All right. So today I'm really excited for today's lecture. I hope you guys are too. So far we've been doing all of this work for this artificial neural network, and finally we're going to do something cool with it. Okay, or at least I think it's really cool. And so we are going to look at the MNIST. All right, let me get your attention. MNIST handwriting or handwritten digit recognition set. Okay, digit. Okay, and so this is now a very famous data set. Get your poll responses in. Make sure you tell me that you're here. And I've linked a bunch of these on CCLE. Okay. And so if you click this, the MNIST handwritten digits data set, it takes you over here. You can download each of these files. They're all pretty large. You're going to have to unzip them onto your machine. And basically, you've got each digit. You've got this kind of this 28 by 28 pixel representation of a number, right? So you got something like this, and and then we're okay, and somehow we are shading this in. Okay, something like that. Okay, so maybe you have the number 4 or something like this. Okay, this in the MNIST data set. Okay, as far as our training data goes, the training data consists of 60,000 rows and 784 columns. Okay, so 28 times 28, this is a 28 by 28 pixel image, and so we have 784 columns. Okay, and the values are on the values between 0 to 255. Okay, so you have basically the intensity of the darkness is on a scale of 0 to 255. So 256 levels of darkness, and there's a total of 60,000 rows. Okay, whenever you're doing machine learning and stuff like that, you need a lot of all of these things depend on a bunch of training examples. And so the MNIST people, they did all of the hard work ahead of us, and they isolated each 28 by 28 image so that it contains only one digit. They've put it all in grayscale, so and they put it into a nice format for us. Okay, and so you can so I've written actually I didn't write this code. I wrote some code for the neural network, but there is code for loading the handwriting data set. I just took this from somebody on GitHub, and it works well. Okay, and so for this, I'm going to set my working directory, and I'm going to run the function. All this does is it's just going to read in the binary data, because when you download the MNIST data set, you have to unzip it, and then it's like these binary files. Okay, so you'll want to, when you unzip the data, you want to get them into this. I put them into the folder MNIST, and then the the data file is a IDX3 ubyte file, which I don't really know much about, but this function handles it. It reads in binary data, okay? And then there's also, huh?
Sorry, what are your double arrows?
Oh, here, because when I'm running, when I do load mnist, when I run that function, what it's going to do is it's going to create variables in the global environment for me to access, okay? This is, because otherwise if it runs inside a function, it just exists in the function, and then as soon as the function is done, it disappears, right? We want to actually work with these things later, so we're going to create the training and the test data in our global environment, okay? And then I run this function show digit, okay? And then, so all we have to do is we just load up the data. So I'm going to run this command load mnist, which someone else wrote for us, which is very nice. And it's going to take the data. I have it saved on my local computer. For it to work on yours, you're going to have to create a little folder mnist and put the IDX3 ubyte files in there, okay? And I'm going to do that, and it loads up the data. It takes a little while because they're pretty big, okay? And it creates test and train, okay? So it's 178 megabytes in memory here. Okay, so let me just explain how this is going to work. We're going to create our neural network. It's a very basic form here. So my input, I'm going to have 784 nodes on my input layer, okay? Lots of these things. And then I'm going to have a hidden layer. And I have arbitrarily chosen just to use 30 nodes, okay? Okay, this is just an arbitrary selection here. And so we're going to have a huge weight matrix, okay? Right? Going from each of these 784 to each of these nodes in the hidden layer. So we've got just this huge, complicated weight matrix, right? So my W1 weight matrix has the dimensions is going to be 784 by 30. And if you wanted to have more nodes in your hidden layer, totally fine, okay? That's completely allowed. And then from our hidden layer, we're going to go to our output layer. And because this is a classification problem, we don't actually want a number between 0 and 1, or we don't want to put it on a scale. We want to say this digit is 0, this digit is 4, this digit is 7, something like that. We're going to have 10 nodes in our output layer. Okay? So going from our hidden layer, we're going to have 10 nodes. Okay, so another, whatever, okay. So you have all these things. So our second weight matrix, our weight matrix 2, what are the dimensions here? 30 by 10, right? We got 30 from our hidden layer, and it's going to our output layer of 10. And each node in our output layer will correspond to a digit, okay? This one will first be 0, this one will be 1, and this one will be 2, so on and so forth, okay? And ideally, what we want, our desired output, if we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, our desired output will all be between 0 and 1, and it'll be something like 0, 0, 0, 1, 0, 0, 0, 0, 0. Okay? For this image, we would say, oh, that's the number 4, and we would hope that the output for this image would be all zeros, and then we would have a 1 at the number 4. Okay? And then, you get a different image, and maybe it would go 0, 1 if the image is a picture of a 1. Okay? this is the kind of output that we want. Okay, and so this is how we can get categorical results from our neural network. Okay. Is this okay? All right, and so I've included a tiny bit of reading. This is it might be a little, maybe a lot of reading. I don't know. It's a it's a website here, okay, that talks about how we can run a neural network for the MNIST data set. It's very good. It's very accessible in my opinion. He explains all of these things about perceptrons, and this is kind of this is what happens if you draw all of the lines. His code is in Python. We're going to stick to our old trusty friend R, and we'll do this, okay? One thing that we did not do in our other neural network that we will do in this neural network is include a bias, okay? So let me just show you how our forward propagation works this time. Okay, so we're going to start with our data, our training data X. Right. And then we will multiply it by our first weight matrix. Okay. And this will form our Z that goes to our second layer. Okay. So far this is the same, right? The difference here is, when we apply our sigmoid function, this is our sigmoid activation function, what we're going to do is we're going to add a matrix of biases. Okay, this is our B matrix here. And I forget. Did I call this B1 or B2? Let me just check my code. I call this B1. Okay, so this is our first matrix of biases. This is the bias matrix. So all we're doing is we're just adding some values to the quantities Z. Okay, so what exactly does adding a bias do, and why would we want to do that? Okay, so when we multiply X by W, we're kind of scaling our X on some kind of, we're doing multiplication there, right? The other thing that we might want to do is, if this is our sigmoid, just recall what our sigmoid activation function looks like. It looks something like this, right? It starts off near 0. As it increases, this is what f of z is 1 over 1 plus e to the negative z, right? So this is what the thing looks like, okay? If I add some bias value, okay, all it does is it just shifts what this thing is, okay? So in actually here my bias is negative, but let me see if I can cut this. Okay, all it does is it just shifts it along. Okay, so if I subtract off some value b, okay, is it just, now it moves it over. Okay, so here, if I subtract off, if right here is at 0, then it moves it along if the bias is negative or something like that. Okay, it just shifts the thing along, and that might be desirable, or we don't have to. We can train it, and the biases could all turn out to be 0. But this allows us to gives us another layer of control in our weights and our propagations here. Okay. So that's what we do. We'll call this, the result of this, our A2 matrix, and then we just continue on just like before. We take our A2 matrix, we multiply it by our second weight matrix, okay, and this is going to give us Z3, okay, And then again, before we apply the sigmoid activation function there to get our predictions, we're going to apply the, we're going to add another layer of biases. So we're going to take our Z3s, we're going to add another set of biases, and this will produce our Y hats. Okay? So all we're doing is we're just moving through the matrix, okay, or moving through the network, starting with our inputs, multiplying it by our weights, and then we are now including a set of biases, set of values, another matrix that we're adding to that, and then we're moving forward there. Okay. Yes, question?
So why do we have the bias in?
So the bias just allows us to give us some finer control. So you can think of it as, you know, when you create linear regression, right, you have an intercept and a slope, okay? So the slope you can think of as kind of the weight matrix. It changes, you're multiplying it by your input value x, okay? But it will only allow you to have this, you know, a certain amount of values, okay? And so if you want to kind of cover the entire space and have all sorts of stuff, you might want to include an intercept. And that's basically what we're doing here. The weight matrix multiplies by our x. We can kind of think of that as our as the slope, and adding a bias as our quote intercept. I mean, of course, it's not, we're not dealing in two-dimensional data here, but it's a similar concept. It just, one is, you know, we multiply it by our input values, and then the other is we're just adding an arbitrary value to our input values. Okay, and these are all just they're just arbitrary values. So so that's what we have. Okay.
Miles,
Yes. Question.
is the loss function optimizing the biases and weights?
Yeah. So when we do our, so this is going forward, and what we want to do is what we're going to want to do is we want to minimize our loss function, right? And so our loss function will be our L, okay? And we're going to just take the difference between y and y hat squared, and we can add that up. We can multiply it by some constant, 0.5 or whatever we want to do, right? So this is what we want to do. And so if we think about applying gradient descent, okay, gradient descent to train, we're going to have, we have a bunch of things to optimize now, right? We now must optimize two weight matrices. And two bias matrices. Okay, so we're basically going to have to find, with respect to weight matrix 1, with respect to, actually I should probably do the bias 1, weight matrix 2, and our second bias. So we have four of these gradients to calculate. Okay, so a lot of derivations to run through. Yeah.
Are the dimensions of your bias matrix and the weights the same dimensions if you're adding them?
So the bias matrix has the same dimensions as our Z matrix, okay? Because we're adding them element-wise, okay? So the Z matrix and the bias matrix, these have the same dimensions. So we can add them, okay? So I guess if we want this, x would be 60,000, or this will just be n by 784, right? Okay, our weight matrix will be 784 by 30, okay? And therefore our z will be n, this one will be n by 30, okay? This one here is going to be n by 30, and this is n by 30, okay? And we apply this, our a is going to be n by 30. Here we have n by 30, our weight matrix is 30 by 10. And so our z here is going to be n by 10. And then so this one is n by 10, this one is n by 10, and this one is going to be 1 by 10, right? No, I'm sorry, this is also n by 10. N by 10. Okay? So that's what we have. Okay. Is this good so far? Okay, so now, so we have an idea how this works. I'm going to skip the calculus here, okay? I'll leave it, I've created a homework assignment for you guys for next week with neural networks. It's a fun one. And so I'll leave it to you to do the calculus in the homework there. You kind of already get the answer because I've written the gradients in code form already, but whatever, okay? I want to show you how this works. Okay, so here we go. We load up the MNIST data, and let's take a look. We're going to look at, let's just say we're going to look at the jth row in our training matrix, and we can see in our training data we have train $y. This is the actual digit, so the second digit is, the second number in our training data is the digit 0. Okay, and then when we look at, this is the vector of 784 values, okay, and we can see there's a whole bunch of zeros. In a few spots it's dark, like around 252, and then other places it goes away, okay? And actually, we can kind of, because the numbers themselves almost look like pixels, I don't know how many, how wide is this? Okay, let's see. Can I get the, I just need to make this a little bit wider. If I can get 28 numbers to fit in here, you'll almost see the digit appear. That's 20. Okay, and so you can kind of see, like, oh, like you can actually see the digit appear in the numbers themselves. But of course, we don't really want to do that. There's a function that that says show digit. Oh, this is not that. That's not the digit. We want digit j. Okay, and we can see. Oh yeah, that looks like the digit 0. Okay, of course, it's probably shaped more like this as a square. And then we can kind of go through and we can just see what was the 100th digit in the data set. That was the number 1, and when we graph it, it looks like this. Okay, so sure, that's great. What we want to do is we want to change the inputs from the digit 1, 5, 9. We want to change it into a set of zeros and ones, right? So I'm running this function called vectorize, and all I'm going to do is I'm going to take I hit something on my keyboard here. I'm going to just set a digit of 0 through 10, and I'm going to just say take the jth digit, or I'm sorry, whatever j is equal to. Okay, so if j is equal to 5, replace in that vector with a 1. Okay, except because we have zeros, we're going to replace the we're adding 1 to everything. So replace the, if it's a 0, replace the first column with a 1. If it's a 7, replace the 8th column with a 1. So here, this is our function vectorize. And all I'm going to do is I'm going to take my training data y, and I'm going to apply this vectorize function. Okay? And this is what it looks like. It says the first 6 rows, it looks like we have successfully done this. And if I compare, the first digit in my training set was a 5, and indeed we see that the 6th column, which represents 5, is now a 1. Everything else is a 0. The second digit is a 0, and in here the first column is a 1. Everything else is a 0. So far so good. Okay, and we can take a look. Okay, so now this is all part of putting in the calculus and getting the derivatives and the gradients. So I need the sigmoid function, sigmoid prime function, and my cost function is just y minus y hat squared added up. Okay, the sum of squared residuals. Yes, question?
Before you use the vectorized function, was
Yeah.
the probability of that number being the image, was it a probability, or did you just
No,
zeros?
this is training data, okay? So it's in our training data set, there's no probabilities. It is, we know that this is the number 5. So there's no probability there. It's a 5. And we are just converting our training data, instead of going from 1 through 5, or 1 through 9, or 0 through 9, we're saying turn it into zeros and ones, okay? And where if it's the number of digit 5, we want everything 0 except the 6th column to be a 1. Okay, so that's all we're doing so far. So far we've done no probabilities, no calculations. Here I'm going to set up my neural network. I'm pretty much using the same code as I had before, and I'm just saying my input layer has 784 nodes, my output layer has 10 nodes, and my hidden layer I'm going to use 30, just an arbitrary number 30 there. Okay. I'm going to set up my initial weight matrix. Here, all I'm doing is I'm just taking some random values, okay? Populating my weight matrix with random values. So it's 784 by 30. My second weight matrix will be 30 by 10. The bias matrix, okay, it's just, we're adding, we have 30 nodes right there, okay? And so here they just need to be the size of the hidden layer or the output layer, okay? And I know over here I said this is going to be n by 10 or n by 30. I'm going to just set it up as a 1 by 30, and I'm going to duplicate it for however many n's I have, okay? So here I'm setting up my biases matrix, B1 and B2, all right? Okay. And here, this is where we do something a little bit different, and this is called stochastic gradient descent, okay? So before, when I calculated my gradients, I took all n rows, right? I took all 60, I would have taken all 60,000 rows, calculated the gradient, and proceeded from there, right? When we calculate all of this. In stochastic gradient descent, I'm saying, well, 60,000, that's a lot, right? That's a huge matrix. It's going to bring my computer to a halt here if I tried to do that all at once, okay? So we'll say 60,000 is too many rows to do at once. And so what I'm going to do is we're going to do stochastic gradient descent. Stochastic just means there's a random part to it. And so what I'm going to say is I'm going to just select 10 random rows out of the 60,000. Okay, we're going to do select 10 random rows. Okay, and we're going to use those 10 random rows to train this one iteration of gradient descent. So I'm going to say, just looking at these 10 rows, calculate what the gradients are and take a step after doing that. Okay, select 10 random rows, find the gradient based on these 10 rows. Okay, and then take a step in the direction opposite of the gradient, right? Okay, and then we repeat. Take another set of 10 random rows and do that over and over again, okay? And so what I'm going to do here is I'm going to first, to set this up, I'm going to shuffle the 60,000 rows, okay? And then I'm going to split them up into 6,000 groups of 10. And then I'm going to just run this process here, okay? Each 10 being a different random set. Okay, so we're going to take the first set of 10 random rows, find the gradient, take a step. Then we're going to go to the next set of 10 random rows, find the gradient, take a step. And I'm going to go through all 6,000 groups of 10, and that way I would have processed all 60,000 images that way. Okay, and that's just one pass. And if I want to do it again, I can do it again. I can shuffle it up and do it again if I wanted to. Does that kind of make sense, that process? Yes, question?
This is strictly for large data.
Yeah, for when you have lots of data, you don't want to, I mean, you could, but your computer will cry if you do, say, take a matrix with 60,000 rows and 784 columns, and now calculate the gradient based on this. It won't be too happy about that. Okay. So here I'm just randomizing this. I'm gonna say we're taking 60,000 rows, and I'm gonna shuffle. I'm shuffling the 60,000 rows. And so we can see kind of what J sub is. It just says, these are kind of the starting point of each of these things. And then we can see, if I set I equal to 1, this is the first one. As far as the rows goes, it's going to start at row I, whatever it is, okay, row 11, whatever, and we're going to go from basically row 1 through 10 the first time. Okay? And then the next time I go through, it's going to go from rows 11 through 20, so on and so forth. And it's pulling from the mixed up rows, which is J. Okay, so J, this is just the shuffled rows of 60,000, and so the first few, I'm drawing row 15,900 and row 22,300, so on and so forth. And then with each iteration, I'm going to say, okay, these are the rows I'm selecting. I'm going to create my X matrix by dividing by 255, so everything's on a scale from 0 to 1. And then we're going to take our vectorized labels. So rather than just the digits, it's the 0 through 1. And then we go through and we do forward propagation. Okay, we multiply by X times the weight matrix. We add the biases, okay? And so the bias is currently just a single column vector, and here it's going to be 30 by 1 column matrix, but my Z here it's going to be n by 30, and so here I'm going to multiply this by a 1 by n matrix, and so this multiplies out to be 30 by n, and we transpose that so it becomes n by 30 as well. So this just takes our biases and duplicates it. We're basically just multiplying it by 1 with the number of rows in our batch size, and it transposes that. So we can add these two together, and we apply the sigmoid function there. We take those results, multiply it by the second weight matrix. We add the second set of biases again, and this produces our predictions y hat. Yes, question? Just an arbitrary thing. I just chose 10. If I wanted to do 50, that's probably fine. The computer can probably do 50 rows or 100 rows without too much problem, okay? Yeah, it's I don't know. I guess as computers get better, you can just say, yeah, do it all, and maybe it can, okay? But you have to think every single time you're taking a step, and so we're going to take a whole bunch of little steps. So here I'm taking 6,000 tiny steps based on 10 each, and basically we're just saying, here's 10 digits, here's 10 pictures, try to figure out what digits these correspond to. Okay, and now we're going to figure out our gradients. Okay, and I've done the hard work here of figuring out the gradients and how to code them up accordingly. Part of your homework is to do the calculus yourself to figure out the gradient, and I'm hoping it'll line up with what we have here. Okay, and then so anyway, so this is the gradient with respect to the second weight matrix, second bias matrix, gradient with respect to the second weight matrix, gradient with respect to the first bias, and gradient with respect to the first weight matrix. Okay, so we calculate all of these gradients, and then we update our current estimates just by taking our current estimate and we subtract off the gradient multiplied by a scalar. I think I've just chosen an arbitrary size of scalar of 1, but you could make it bigger or smaller, whatever. Okay, and that is the gradient descent matrix. All right, gradient descent algorithm. Is that okay? So it's pretty much everything we did last time with the neural networks, except now I have these bias matrices that I'm also trying to optimize, and all we had to do was calculate the appropriate gradient for those, and we're just going to do the same thing. We're just going to take our current estimates, subtract off the gradient, take a step in the direction opposite of the gradient. So if I do one pass of this, basically I'm going to run through 6,000 groups of 10 images. 6,000 groups of 10 images, and it will work. Okay. I'm going to skip this part. There's always a good idea to do some numeric gradient checking to make sure your thing is correct. You guys maybe will just take me at my word and say I did it and it's correct. Okay. So let me just kind of show you what kind of predictions we're getting. So before I do any training, I can take kind of our inputs and say, these are our x, and with our current weights that we have, what is my y hat? We look at this, and this, you can't even make any sense of it. Let me just round off y hat to 2 decimals here, okay? And currently, this is what it's supposed to look like, is a whole bunch of zeros and a 1 in one of these columns, okay? And right now, because we haven't done any training, this thing looks like garbage, okay? It should not, what we want is a whole bunch of zeros, and then in one of these columns there to be the value 1. That's what we want, okay? So I'm going to go ahead and run through this loop, going through all 60,000 things, okay? So it's running right now, and then, so it's doing, groups of 10, and now it's done, okay? And that's it, okay? So there's no like brain here. All we're just saying is here's some data, look at this, calculate the gradient, take a step here, okay? Now let's take a look at what our thing looks like, okay? So let's take a look at what our data might look like. So here we're going to take some rows out of X, and we'll apply it, and we'll take a look at what kind of predictions we're getting right now. So this is y hat. Again, it looks kind of crazy. So let me just round off y hat to 2 decimal places, okay? And we see, what do we see? In this first row, we see a whole bunch of zeros, and then this, what do we call this? This column has a 0.99, so basically a 1, and everywhere else, it's pretty much a 0, okay? In our second row, we have a whole bunch of zeros everywhere. This column has a 1, and everywhere else, it's also a 0, okay? And we're getting pretty good results, okay? Pretty much every row has mostly zeros or something very close to 0, and then one column is close to 1, 0.97 or something like that, Maybe in some of these rows we're having something that's a little bit off from 0, but by and large, generally there's only one column where there's a 1, okay? And this is probably not the best way to do it, okay? But if I just round off to 0 decimal places, okay? Here we see, basically just one value of 1 in each of these columns here, okay? And you do run the risk that it's possible that based on the results, none of the values get predicted to 1, that you have multiple zeros, or it's also possible that you'll have things, that multiple things will be predicted. Like it might predict it is equal to a 4 and a 9 or something like that. So this was our y hats. Let's take a look at what the actual y's were. Okay, so the actual y's for our selected rows is this, and let's convert this. So to convert it back into the digits, how can I convert this row of zeros and ones back into digits? Okay, well, I can just multiply it by the matrix 0 through 9, right? Okay, and so these are my predictions, y hat, and then the actual values that we used, the actual y's, they look like they match. Let me see if I can C-bind these together. So I'm going to compare my y hat matrix, my y hats. These are the predictions from our neural network versus the actual values. Okay, and what we see is that they match exactly. Okay, this should be super impressive. Okay, in that, remember what we did there. If we think of how this neural network works, okay. This is all it's doing. It's just taking some input values, multiplying it by some numbers, adding some numbers, applying a function, and it spits out a thing. Okay? There's no actual brain or thinking or cognition here. Okay? However, I just said here's a bunch of numbers. This number's a 4, and this number's a 5, and this number's a 7. Figure this out. It runs through all 60,000 images. And now when I come back here, it's saying, well, I'm predicting it's a 3. What is the actual value? It's actually a 3, okay? And we can go through and we can just kind of test the performance on the actual test data here, okay? So here I'm going to take, 1,000 rows out of the test data set, okay? And we'll do just kind of all 1,000 rows, and we'll go through, and these are the guesses. Okay, so our guesses these are the 1,000 guesses that it has. Okay. Okay, and here it's guessing 16. This is obviously not correct, and that's because it probably guessed this one might be a 9 and this one might be a 7 or something. Maybe it got mixed up, and the way we have it figuring out the process, it's a very rudimentary way. Okay, but we can compare our guesses to our actual results, and we'll create a table. Okay, and so when it was actually a 0, it guessed 0 85 times. And it guessed 0 other times. These are probably times where it couldn't figure out which one. None of these probabilities rounded up to 1. Okay, when it was a 1, it guessed a 1 125 times. Okay, when it was a 2, it guessed a 2 105 times. And some of these things, it makes some mistakes, okay? But by and large, and this is just after one pass of 60,000, okay? I could further improve my my weights by doing a second pass over the same 60,000 images or something like that, okay? We can keep improving our weights, so on and so forth, but this is just doing 10 at a time, taking a bunch of these, and now we are successfully recognizing digits for the most part. Okay, we can kind of see out of our 1,000 results how often we can see, how often did our predictions differ from the true value. Whoops. Okay, so out of 1,000, okay, it made a mistake 101 times out of 1,000. Okay, so we're getting around 90% accuracy as far as we give it a 28 by 28 image, and we say, what number is this? It takes a guess. Okay, we're correct about 90% of the time. It's not perfect, but again, we only trained it on just one pass of the 60,000 images. We only had 30 nodes in our hidden layer. So there's a lot that can be done to further improve it, but I thought it was pretty neat. Okay, I hope you think it's kind of neat too. I've posted up a homework assignment where you'll take a stab at this using the good old IRIS data set here. Okay. The homework's available in week 4, and it'll be due 1 week from Monday.